Credit analysis models. This is a fairly long reading focused on credit analysis. In section 2, we learn what exactly credit risk means and how to model credit risk. We also learn how to calculate the credit valuation adjustment. This is a very important calculation, so make sure that by the time you are done with section 2, you know how to calculate the credit valuation adjustment because this is used throughout the reading. Section 3 deals with credit scores and credit ratings. Here it's important to understand the distinction between the two. Section 4 gives a high-level overview of structural credit models and reduced form credit models. You need to understand the assumptions of these models. You need to also understand the strengths and weaknesses of these models. Then Section 5 focuses on valuing risky bonds in an arbitrage-free framework. So this section builds on what we do in Section 2. In Section 2, we assume an interest rate environment where interest rates are not changing and we have a flat yield curve. Whereas in Section 5, we now assume that interest rates are volatile and we also assume an upward sloping yield curve. So this really builds on the material from Section 2. In Section 6, we interpret changes in credit spreads. So we try to understand what are the components of credit spreads and then why do spreads change. Section 7 has to do with the term structure of credit spreads, and then Section 8 deals with credit analysis for securitized debt. Modeling credit risk and the credit valuation adjustment. The first term that we need to understand is credit spread. This is also called the G spread. The credit spread is equal to the spread or difference between the YTM or yield to maturity on a risky bond and the YTM on a government bond which is considered risk-free. The maturity of both these bonds needs to be the same. So for example, if we have a 5-year corporate bond with a YTM of 6%, and a similar 5-year government bond with a YTM of 4%, then the credit spread is equal to 2%. This is also called the G spread or government spread because we are talking about the spread over a risk-free government bond. The credit spread is a measure of credit risk. The higher the spread, the higher the credit risk. We also need to draw a distinction between credit risk and default risk. Often these terms are used interchangeably, but in this reading they are considered different. Default risk is a narrow term focused on the risk of default. Credit risk considers the default and it also considers the loss if there is a default. Now to illustrate the distinction, let's say we have two bonds A and B. It is possible that A has a higher default risk but a lower credit risk. And that might be because A has substantial collateral. So let's say that A's default risk is 2%, whereas B has a default risk of 1%. But A has a lot of collateral. So if there is a default, the loss will be very little. On the other hand, with B, the probability of default or the default risk is relatively low compared to A, but let's say that if B defaults, then everything is lost. So there is no recovery. In that case, we can say that even though A's default risk is high compared to B, but the credit risk is relatively low. Next, we come to the factors that are considered when modeling credit risk. There are three major factors. The first is the expected exposure to default loss. This is the total amount that can be lost. And let's understand this through a very simple example. Let's say that we have a 1-year bond which has a par value of 100 and this pays a coupon at the end of the year. The coupon rate is 4%. So if we are at time 0, this is time 1. The total cash flow at the end of year 1 is 104. This is the expected exposure because the worst case scenario is that there is a default and this amount is not paid. So 104 is the expected exposure. Next we come to the recovery rate. This is also called the loss severity. So if there is a default, then how much can be recovered and what is the loss? If we say that the recovery rate is 40%, then what that means is, if we do have a default, then the amount that we will recover will be 40% of 104, which is 41.6. If there is no default, then we will get the entire 104. Now, from the recovery amount, we can also calculate the loss given default. So the loss given default will be 60% into 104, which is 62.4. The total amount, 62.4 plus 41.5, should be equal to 104. So we could also have calculated this number, 62.4, by taking the total exposure amount, which is 104, and subtracting the recovery amount, which is 41.6. The third factor to consider is probability of default. Let's say that the probability of default is 1%. Then we can calculate the future value at the end of year 1 by saying that there is a 99% chance that there is no default. So we can do 104 into 99%. And then there is a 1% chance of a default. So we take 41.6, which is how much we would recover if there is a default, and then multiply this by 1%. When we do this calculation, 41.6 into 1% plus 104 into 99%, we get 103.376. So this is the expected value at the end of year 1, given the actual default probability. To come up with the present value at time 0, we take this future value and discount at the risk-free rate. Let's say that the risk-free rate is 3%. So if we discount this number by 3% for 1 year, we will get 100.365. But this number, 100.365, is different from the observed value of 100. Why is that? The reason is that in coming up with this future value, we took the actual default probability of 1%. In order to come up with the observed value of 100, we should use the risk-neutral default probability. So what is the distinction between the risk-neutral default probability and the actual default probability, and why are they different? The actual default probability is the probability that is calculated based on historical data. This actual default probability does not include the default premium associated with uncertainty over the timing of possible default loss. Now, in this particular case, we had a very simple scenario where the timing of default loss was at the end of the year. But if we have a multi-year bond, then the timing of default is uncertain, and the actual default probability does not account for that uncertainty. Another reason for the difference is that the observed spread over the risk-free bond includes liquidity and tax considerations. So the point is that there is a difference in the YTM of a risky bond and a risk-free bond based on credit risk, but that spread in the real world needs to be increased to account for liquidity factors and tax considerations. The liquidity of corporate bonds tends to be lower than the liquidity of government bonds. That's why we need to make an adjustment related to liquidity. So the question now is, how do we calculate this risk-neutral default probability? Let's say that risk-neutral default probability is denoted by P star. We want to calculate this P star such that the present value is 100. So if we have P star, what is our future value? So let's go back to the same simple bond where we have time 0, time 1, and the cash flow at the end of year 1 is 104 if there is no default, And if there is a default, then the cash flow will be 41.6. So what is the expected value at the end of year 1? That expected value will be